cause about 0.8 seconds of delay, whereas 5 attackers can cause about 1.8 second delay. So how does this translate to the impact on applications? Well, a typical delay-sensitive application is voice over IP. Voice over IP is very delay-sensitive. Ideally, you want the delay to be less than 100 milliseconds. If the delay is between 100 milliseconds and 400 milliseconds, it's tolerable. But your voice quality will degrade. However, if the delay is more than 400 milliseconds, people believe that the voice over IP application becomes useless. Okay. Well, now you can see that if there's only one attacker in a cell of 50 users, the average delay is about 800 milliseconds. That's way over the tolerable delay in voice over IP applications. In the 4th generation cellular networks, voice will be carried over data. Okay. So, well, fortunately, currently the 4G 4th generation cellular networks, they demand that the voice data have a higher priority than other regular data. Okay. But if they had not designed that in such a way, then you can see what would happen. Because in that case, only one attacker in a cell of 50 users can disrupt all the VoIP applications. Okay, so now we understand the impact of the attack. What can we do about it? We can try anomaly detection. We can monitor the average throughput of every cellular user. Okay, based on the assumption that no user should have super good channel quality that it grabs more than, say, 50% of all the slots. Okay, but what if there's a cell with only 2 users and one user has a better channel quality than another user? Well, you have to modify your anomaly detection algorithm to say that, okay, if there are fewer than 5 users, then that's okay. But if there are more than 5 users, then no user can grab more than this number of slots. Yeah, no matter what you do, you can always find some corner cases where you have to modify your rule again. Okay, so it might help, but it's not an ideal solution. You can also try to do anomaly detection based on the number of handoffs. Remember that the persistent attack based on frequent handoff among different cells. Typically, this should not happen, right? Because you hand off only if typically we hand off when you drive, when you move. So you move from one cell to another. So you can say that, well, a cell phone can have more than one handoff per 10 seconds. But then what if a cell phone happened to sit on in the overlapping area of 2 cells? And due to some random interference, suddenly one cell becomes better than the other. So this cell phone just hands off very frequently, but not for a malicious reason. So you might have some false positive thinking that this cell phone is attacking your network, but whereas it really isn't. So once you start to do anomaly detection, you get all into this very hairy area of how do you have a good rule that don't cause a lot of false positives. So we try to devise an approach that does not have these problems, that solves the root of the problem. And even better, we wish to prevent this problem from happening in the first place. But remember, there are 2 vulnerabilities that are roots of the problem. The first is that the base station does not verify the channel condition report by the cell phone. Well, we are not aware of anything that the base station can do to verify that. Right? Because you have to measure this channel condition at the location of the cell phone. Since the base station is not at the location of the cell phone, so there's not much that the base station can do to verify the report. However, the second root cause is that the proportional fair algorithm does not guarantee fairness across all cells. It guarantees fairness only within a single cell. So therefore, if we can extend the proportional fair algorithm to guarantee fairness across all the cells, then we could have prevented this problem from happening in the first place. So the approach is very intuitive. Once a cell phone moves from one cell to another, its average throughput should move with it. Okay. And this is not too difficult to implement, because once a cell phone moves from one cell to another, some other information has to move with the cell phone as well, such as how many minutes it has used from the previous cell. So we just want to add this additional information to move with the cell phone. You might think that this is so trivial, but it's not as trivial as I just described, because you can't just copy the average throughput over, because different cells may have different users. Intuitively, in a cell with fewer users, each user will have a higher throughput, average throughput, than another cell with more number of users. All right. So when you move this average throughput over, you have to scale the average throughput by the number of users in the cell. Moreover, average throughput is also affected by the average channel condition in that cell, because once channel condition gets better, throughput increases. So you also have to take into consideration the average throughput of a cell. So we used this formula as an estimation of an average throughput in a cell. So this is the first term, is the estimation of the instantaneous channel quality. This term is the gain of that cell. Typically, people use a log n as a rough estimation of the gain. And here n is the number of users in the cell. So this is the formula that we used to calculate the average throughput of a cell phone between two cells. Okay. So you plug in the formula from before, and remember that when a cell phone moves from one cell to the other, it's at the border of both cells. Right? So its channel quality its instantaneous channel quality should be similar in both cells. So therefore, these two terms cancel out, and here's what you get. And we know the number of users in each cell, and the gain is approximated by log n. So we know how to calculate this value. And once we know if the user moves from cell A to cell B, since we know it's the user's average throughput in cell A, then using this formula, we can calculate its average throughput in cell B. Okay, so our related work. There have been some work on looking at attacks on scheduling in cellular data networks. So this is one particular work from Sprint Labs. Instead of attacking the scheduler by reporting false channel quality information, they do not modify the cell phone at all, but rather they try to attack scheduling indirectly by using bursty traffic from the application level. So what they do is that they have two laptops connected to a test cellular network inside Spring Labs. And one laptop is a victim user, the other laptop is an attacker. So the attacker will remain silent for a while, which meaning that it does not send any traffic. And suddenly, this attack laptop sends very bursty HTTP traffic. So this would cause the scheduler to give this attack laptop a lot of scheduling slots. Okay. So this would result in the starvation of the victim laptop. However, since they don't hand over, their attack is not that effective. Remember I said before that the fewer number of users in a cell, the less scheduling slots that the attacker can get. Okay. So